Hi, in this lecture we are going to look at the polar representation of complex numbers. Okay, so in polar representation there are two parameters of interest that we must find for a given complex number z equals x plus yi. One of this is what we call the modulo. Now this modulo is the same as the magnitude of this complex number when represented in the complex plane, and the second parameter is the argument. Now the argument is the angle that this complex number makes with the positive direction of the x-axis, so it's basically an angle. In the complex plane, as we saw earlier, for a particular complex number z having real component x and imaginary component y, let me extend this up a bit, and an imaginary component y, then this is our modulo, the straight line to the end over here. So the magnitude of z, let's call it r, and the principal argument is the angle we are talking about, theta, making with the x-axis. Okay, so let's make some deductions over here. So first of all, the magnitude of the complex number, let's see some identity squared being equal to this multiplying its conjugate. So when you multiply a complex number and its conjugate, then what you get is the square of its magnitude, and that can be proven algebraically. And also, let's go back to the complex representation where we had this and that. So z is here, theta is here, r is here. Okay, so now when we know theta and r, which are the two parameters of interest when we talk about the polar representation of a complex number, when we have these two parameters, then we should be able to get back the individual components, which are the real components and the imaginary components. So given r and theta, we should be able to get x and y. Now this goes down to basic trigonometry. Okay, so this is our x and this is our y. Now from this diagram we can draw some basic mathematical relations using trigonometry. Now r is equal to square root of x squared plus y squared. Theta is equal to tan inverse of the imaginary part over the real part, y over x. Now getting x, so this is when you have x and y and you want to find for the modulo and then the argument. Now x from r and theta. Now let's go back to hypotenuse and the adjacent and then the opposite stuffs we know from basic trigonometry, and especially the theory of Pythagoras. So x will be equal to the hypotenuse. So okay, here we are using a small r, so that's that. Now what we are looking for is x, which is what is adjacent to the theta. So it's a cosine, so cos of theta, and then the y, which is opposite the theta, we get it from sine of the theta. Now once again, getting theta when you have your complex number in the coordinate form x and y, can be confusing if we don't have the complex number in the first quadrant. So for instance, we have a complex number, say, represented in this form, where the complex number maybe is over here. When you do so here, it means the real part is going to be a negative number and the imaginary is also going to be a negative number. So let's do negative x and negative y. So for such a complex number, when you compute, for example, tan inverse of let's say -3 over -2, let's check what a calculator gives us. Tan inverse of -3 divided by -2. So the answer we get is 56.31 degrees. Now 56.31 degrees, it means this is what we are talking about. This theta, 56.31 degrees. But then the angle we are looking for is the angle from this x-axis all the way to here. So, and obviously it's very big. It's bigger than 56 degrees. A bit greater than 180 degrees. So what we will do is that when you are given a complex number in this coordinate form and you want to get the argument, what you need to compute first is the reference angle. When I say reference angle, it means the angle that the complex number makes with the x-axis, which is the horizontal axis. So first, let's find that reference angle. So it is the acute angle made with the x-axis. Then from where the complex number is, then you know what to do in that reference angle to get the actual angle you are looking for. So in our case, where the number is here, the complex number is here, after solving for tan inverse of -3 over -2, then we are getting 56. So we use the positive values. In computing the reference angle, you use the positive values to solve for it. So even though here might be, let's say for example, -3 and 2, and here might be -3, when we are solving for this reference angle, then we use tan inverse of 3 over 2. Whatever answer we get over here, in this case 56.31 degrees, then this is the angle we've made with the x-axis, which is an acute angle. Now we know that this is the angle obviously we are interested in, from the positive x-axis all the way to this. This is what we call our argument, the principal argument. But we know that from here to here is 180 degrees. That's 2 quadrants. So 180 degrees, then we just add it to that to get our argument. Okay, now let's take another complex number. This time in the 4th quadrant. So here, when we solve for the reference angle, we'll get this angle. Let's say theta ref. Then this is the angle we are interested in to call our principal argument. So here it's simple. It's either we add 270 degrees. So from here all the way to this quadrant is 270 degrees to this remaining angle. Now this remaining angle can be gotten by 90 minus the reference angle we've calculated for. But that might look a bit longer than just subtracting this reference angle from 360. We see that the entire argument we are talking about is just this reference angle short of 360 degrees. So we can just compute our argument by doing 360 minus that reference angle we've calculated for. So in computing the argument, you have to be mindful of where your complex number is, in which quadrant it is. Then you solve for your reference angle, and you have to come up with how you use this reference angle to actually arrive at the actual arguments you are looking for. Okay. Alright, so the next thing we'll talk about is the triangle inequality. Now, triangle inequality still we have to do about addition of complex numbers. So for z1 plus z2 is equal to another z in the complex plane, let's represent that by this. So let's say this is our result, then we have this and that. Okay, so we can get that. So this is z1 and this is z2, and this over here gives us z1 plus z2, which is the z we are calling over here. Now, what is this triangle inequality trying to tell us? The triangle inequality is trying to say that, so first of all, let's go back to normal plane geometry before we come back here. Now, the triangle inequality, when you have a triangle, let's say sides A, B, and C, and let's denote C as maybe that's our longest side. Now, C, and let's call it our resultant for these two. So C is the resultant of A and B. So A plus B is equal to C. So let's say it's a vector, A plus B, giving us the C. Now this is why the triangle inequality applies. That the magnitude of A plus the magnitude of B should be greater than or equal to the magnitude of A plus B. Now, A plus B is the C over here. Now, when we take the individual magnitudes and sum them, it should be greater than or equal to when we take the magnitude of the summation of the two vectors. Okay, so when we extend this into the complex numbers, then we can say that the magnitude of z1 plus the magnitude of z2 should be greater than or equal to the magnitude of z1 plus z2. So in a complex plane, whenever I have two complex numbers, you can't expect that the magnitude of the resultants should exceed the summation of the magnitude of the individual complex numbers. It's not going to be possible. Okay. So as seen over here, as I was explaining earlier, when we should sum A plus B, so the magnitude of A, so this is how long A is from here all the way to here. That's how long A is. We can see that when we couple it with the length of B and compare it to the length of this C, maybe the C might not even be as long as it is, but C, we can see that the summation of, so this one represents magnitude of A plus magnitude of B, and consider it is obviously greater than the magnitude of C, which is C, magnitude of C is the same as magnitude of A plus B. Now this, the case where they could even be equal, that's at all, a case where they could even be equal is when we even have a degenerate triangle. And when I say a degenerate triangle, that's something like a straight line. So let's look at something. So from this point, we have A, B, C, where we can see that obviously when we add these two lengths, it should be far longer than C. Checked. Let's do something like this. When we have A, B, C, when we add these two lengths, it's going to be greater than this, obviously, but it is kind of approaching it. They are getting closer. Still checked. The worst case is when we have something like this. So something like this. This length, which is the C, is almost becoming equal to the summation of this length A and B. So the worst case when we have a degenerate case where the AB collapse into the C in that place. So let's say these are A is starting from here and ending somewhere here, A, and then B is starting that place and ending here, but C is the entire thing. Then here we can see clearly that A plus B, that's the magnitude of A plus the magnitude of B, is equal to the magnitude of C. So that's the worst case, that they will be equal. So that's basically what the triangle inequality is all about. Let's look at multiplication and division in the polar form. Multiplication and division in the polar form. Multiplication and division in the polar form. So the polar form, as we saw, Z is equal to R. So before I write this, we saw that Z is equal to X plus YI, and we saw that when we have R and theta, then Z is equal to X, which we solved for to be R cos theta, and Y we solve it to be equal to R sin theta, then multiplying your I. So we can put the I before everything. So Z to be equal to, and we can factorize R2 out, then R will be equal to, so Z to be equal to R multiplying cos of theta plus I sine of theta. So this is it. Alright, so let's multiply. So when we want to multiply two complex numbers in this polar form, it means we are going to do something small. So let's say, for example, Z1 is equal to R1, always making I with 1. Okay. R1 multiplying cos of theta 1 plus I sine of theta 1. Then Z2 is equal to R2 cos of theta 2 plus I sine of theta 2. And we want to find Z1, Z2. Now we've already done this when we had the complex numbers in the X plus YI form, and we went ahead to expand. So it's basically the same thing we are going to do over here by expanding this as well. Okay, now let's expand the product. So when you should expand this product, Z1, Z2, then we are going to get R1, R2 multiplying, now there's two brackets to multiply. We have cos of theta 1 plus I sine of theta 1 multiplying cos of theta 2 plus I sine of theta 2. So this is catered for. Now this is where we are coming to focus on. So we are going to use distribution. So we'll distribute this and that, and then we'll distribute this again on that and that. So we are going to apply distributive property over here to solve for what's in the bracket. Okay. so let's keep that in mind. So we have cos squared, so sorry, cos theta 1 cos theta 2. So cos theta 1 cos theta 2, which is the first term, then cos theta 1 multiplies I sin theta 2, so plus I, so let me do cos theta 1 sin theta 2. Then continuation, we'll have I sin theta 1 cos theta 1, then plus I squared. Now in this case, two items are coming to multiply, so the I sin theta 1 and then I sin theta 2 are coming to multiply. So we have I squared sin theta 1 sin theta 2, and we already know what I squared is, which is -1. So when we do this, we get cos of theta 1 cos of theta 2 plus these 2, so I multiplying, so I into bracket cos theta 1 sin theta 2 plus sin theta 1 cos theta 1, then minus sin theta 1 sin theta 2. So at this point, we are coming to apply trigonometric identities to solve for the rest. Now the two we can identify is this 2 form an identity, and this in the bracket also forms an identity. Now this part is an identity of cos of theta 1 plus theta 2, and this also is I sine of theta 1 plus theta 2. So in short, when we are multiplying two complex numbers in the polar form, then what we are getting is their modulo will multiply r1 r2, then we have the real part giving us cos of their sum of their argument, which is theta 1 plus theta 2, then plus I multiplying sine of the sum, so theta 1 plus theta 2. So this is how we multiply two complex numbers in the polar form. Now it can also be proven that when you are dividing, then it should follow that we will have their modulo dividing, and for this we are going to have their arguments subtracting, I sine of the difference, so theta 1 minus theta 2. So this is how multiplication and division of complex numbers is done in the polar form. The next time we meet, we'll talk about powers of complex numbers and the De Moivre's theorem. Until then, see you. Don't forget to like this video, comment, and share this video as well. Thank you.